Good morning. My name is Sonja Glavaski. I'm a program director at RPI. My talk will be a little bit more technical in the sense of what we are trying to do in accelerating, bringing some of this technology closer to the market and deployment. And I'll specifically talk about the program that I've established and that I'm managing. It's called NODES, which stands for Network Optimized Distributed Energy Systems. And in short, this is controlling the grid edge, some of the stuff that hasn't been discussed yet. So as some of the previous speakers have already discussed, the way how we run grid is we have at the transmission level, at the high voltage level, bulk power plants that can be either renewable or non-renewable, and then we have large consumers that are connected either at the transmission or sub-transmission level, and then we have distribution. At the distribution level, there's a lot of change going right now. And this is one of the entry points for some of the renewables that were mentioned earlier. Solar is mainly entering at the distribution level, and this is where some trends that you may be hearing about decentralization and distribution of the power grid are happening. So what is, for the sake of the rest of the presentation, I'll call everything that is happening at the distribution level distributed energy resources that encompasses both the generation, storage, and smart loads. So the way how we manage grid right now, we do it top-down. We basically dispatch power generation to match the load, and we control only generation. We do not control consumption, very little in very few spots. And what is one of the well-accepted paradigms in operation of the grid is that anything on distribution level is called net load. So that is basically a load that we need to serve minus any power generation that we have locally. And in the current power system community, they think of pure load as a positive and generation negative. And then what they are trying to do with distribution of the power all the way from transmission down to the distribution level is match this net load. All this by also obeying the laws of physics at any point in time where you have to exactly match the power generation with the consumption, otherwise we'll have instabilities happening in the network. Right now we have very little visibility in the net load in what's happening in distribution level, and we also, to make sure that grid is run reliably and that consumers are happy, we plan for the peak load. I think there is no doubt by now that we all understand consumers in the United States want renewables. 29 states and DC do have renewable portfolio standards that are more or less asking for 20 to 30% of renewables by on average 2030. And what are the challenges with renewables grid integration? So we are going for a paradigm that I showed you where we dispatch bulk power generation to cover relatively predictable load. And we also have built a large transmission network that has capacity available in unforeseen events to reroute power and take care of any potential blackouts. Now we are dealing with intermittent distributed generation that Professor Abt has discussed. Then we have variable net load, and variability is caused not only by a variability of the power generations, mainly solar that we are connecting to distribution, but also changes in consumption patterns. So we are, for example, having a rise of electric vehicles in some portions of the country, and that is affecting the shape of the net load. And then at the same time, we have built power plants at the locations that we didn't originally plan them for. So you have large wind farms and concentrated solar plants in the locations that were not planned, and that may cause issues with the capacity of a transmission network. Multiple studies have been done, and the conclusion was that to reliably and cost-effectively deploy renewables, we cannot go beyond 30%. I do not have time right now to go into details why that is, but we did do a deep dive at the agency, what is the root cause of this, and then we postulated that if we can actively control net load, then 50% renewables and higher will be possible. And what I mean with this, that we actually control generation, storage, and smart loads all at the distribution level, and coordinate them with the rest of the power grid. So this is what actually had us establish the NODES program, where we are trying to develop technologies mainly based on optimization and controls that will reliably manage dynamic changes that are happening in the grid by leveraging devices that we already have on the grid or that consumers are installing, such as distributed energy resources and flexible load, and that while we are doing that, we are actually providing an ancillary services to the grid. What that means in short is that we are keeping stability of the grid with the change of a mix in the generation, and then also different types of patterns of consumption. And we want to do all this while we are also guaranteeing level of service to the grid, so we develop a trust in grid operators that some of the capacities that they are expecting today from the generation they can actually get from the net load and resources that are located in the parts of the grid that we are not used to, and also guaranteeing consumers the quality of service. We separated technologies in 3 different bins based mainly on time scales in which they have to provide services to the grid, and you can think of these as 2 different types of categories of projects. One is developing what we call synthetic inertia, basically providing autonomous response to changes in the frequency by loads and DERs, and challenges are many, but the ultimate goal is to keep the system stable. And the next 2 categories are talking more about reshaping this net load, either coordinating or shifting both generation and storage and loads in different time scales. So category 2 is something that we want to like to do in the time scales between like 5-10 seconds up to half an hour. And this is where we are doing a lot of coordination, and we are still focused on distribution system. On the right hand, in the right-hand corner, I'm actually showing you the lead organizations who are receiving funding from the agency to do this research. And the third category is providing a reserve by reshaping and shifting in longer time scales between 10 minutes to up to 3 hours of loads that do have significant portion of storage, and then also shifting on non-critical loads to support frequency, recovery, and reliability. And what the challenge here is that this category has really to be closely integrated with the transmission level power generation. For each one of these categories, we have specified validation scenarios. For first 2, we actually ask our teams to validate technology with physical devices, at least 100 physical devices in advanced laboratory or field tests. And as the program is progressing, we are raising a lot more visibility for the teams, but then also getting a lot more interest from some of the industry, and we are adding more elaborate test capabilities. I'm just showing you 12 teams that we are funding, these organizations that are comprising these teams, and also I am showing you which categories are they looking in. We have just one team who's specifically looking in category 1, synthetic inertia, and we have several other teams that are looking into categories 1 and 2. And all this being said, we are in the 2nd year of the program, so we're seeing already some nice advancements. And as I mentioned, we are being asked to actually conduct more elaborate validation of the technology in the field. So what we see as outcome is increased renewable integration, a streamlined DR deployment, and the way how we are doing it, we are also trying to improve architecture of the grid at the distribution level and improve grid resiliency. And all this while managing system reliability and consumer costs. We are RPI. So thank you for listening, and I'll pass the baton to Frank.